It's my great pleasure to introduce our today's speaker, Professor Ivkovic. I don't see the title of his talk, but he will demonstrate his presentation soon. Yeah, it's here now. And at the end, we also will have a small surprise for all of you, thanks to Professor Ivkovic, who is not only a great mathematician, but he is also very well doing with piano. But we will see. Okay, first with mathematics. Let's continue with mathematics again. So it's my great pleasure, Professor Stefan Ivkovic. Thank you for agreeing to deliver a lecture at our seminar. And please go ahead. Thank you.
Many thanks for the kind words. It is also my pleasure to have opportunity to share with you my recent results. So yes, as you can see from the title, I will speak about topologically semi-transitive operators on Banach spaces. Before starting speaking about the results, I would like to mention that actually it is a quite recent preprint, which I have posted on Archive. But in fact, it is based on my previous published papers, which are already announced in the abstract. So in my previous published papers, I considered some concepts from dynamics of operators, and here are some more general concepts. And the proofs for these new results are actually mainly based on the already published proofs, but there are also some new ideas which have been needed in order to consider these more general concepts. And before starting speaking about the concrete results, let me just say about some two definitions, two general definitions from the dynamics of operators, which will be crucial in our talk. So if X is a separable Banach space and we have a sequence of bounded linear operators on X, then this sequence is called supercyclic. If there is an element X, which we will call a supercyclic vector, such that this set is dense in X. And then the set of all supercyclic vectors for such sequence of operators will be denoted by SC. This is just the notation. And if this set of all supercyclic vectors for this sequence happens to be dense in X, then this sequence of operators is called densely supercyclic. But we are not going to be interested in arbitrary sequences of operators. We are actually going to consider the powers of a single operator. So a single operator T in Bx is called densely supercyclic if this sequence T to the power n, when n runs through natural numbers, if this sequence is densely supercyclic. But there is another notion which we can consider in general Banach spaces, and it is so-called topological semi-transitivity. What is that? So if you have a bounded linear operator on a Banach space, then we say that T is topologically semi-transitive on X if for each pair of open non-empty subsets O1 and O2 of X, there exists some natural number n and some scalar, non-zero scalar, lambda, such that lambda Tn of O1 intersected with O2 is non-empty. In the literature, people also use the notion topological transitive for supercyclicity. However, I prefer this notation topologically semi-transitive. Why that? Because if you drop the assumption that you consider a scalar, arbitrary scalar lambda, but you require that this lambda is 1, that means that you require that Tn of O1 intersected with O2 is non-empty, then we say that T is topologically transitive. So it was natural to me to say that if we consider for a more general scalar lambda and not just lambda equal 1, then we have something weaker than topological transitivity, so it is natural to call it topological semi-transitivity. But why people do call it topological transitivity for supercyclicity? Because Actually, in separable Banach spaces, these two notions are equivalent. So an operator T is topologically semi-transitive if and only if it is densely supercyclic for separable Banach space. And this was the reason why I introduced now both these definitions. But from now on, we shall just consider this concept, which can be considered for general Banach spaces. But please keep in mind that for separable Banach spaces, these two notions are equivalent. And now we are starting to speaking about our concrete results. The setup is the following. So we shall consider A to be a non-unital C-star algebra, and A is a closed two-sided ideal in a unital C-star algebra A1. And then we assume that we have an isometric star isomorphism phi of A1, which in addition satisfies that phi of A is exactly equal A. And also we assume that we have a net in this A consisting of self-adjoint elements, which are in the norm all less or equal to 1, and such that in addition, if you consider P alpha squared, then this net is an approximate unit for A. So A is non-unital, but we assume that this is an approximate unit, that you have such net, such that this is an approximate unit for A, and such that the net consists of self-adjoint elements with this bound. Now, we assume in addition that our isometric star isomorphism is such that given any alpha fixed index alpha from this net, that we can find some natural number n alpha such that this relation holds for all n greater or equal to n alpha. Now, of course, notice that this depends on alpha. So for each fixed alpha, we can find some n alpha depending on alpha, such that this holds for all n greater or equal to alpha. And passing to the adjoints, you will then observe that also this relation holds because pi alpha is assumed to be self-adjoint for all alpha, and f is assumed to be a star isomorphism. So by taking star of this, you get this, and then you also have 0 by the assumption. So we want to have this special isometric star isomorphism and this net, which is indeed an approximate unit. And then we choose a B invertible element in A1, and then we define the operator T phi B on A1 in this way here. So it is actually a composition of two operators. First, you consider this isometric star isomorphism, and then you multiply from the left by B. And this operator is well defined on the whole A1, not just on A. But, and it is a bounded linear operator on A1. But since A is an ideal in A1, one can check that this actually holds, that A is invariant under this operator, simply because phi preserves A. So phi preserves A, and then if you multiply by B, you simply stay in A, because A is an ideal in A1. So this is our setup, and as you can guess, we want to answer the question, when are the operators of this kind topologically semi-transitive? And here, okay, before speaking about that, I should just say that we can also calculate explicitly the inverse and the powers of these operators. This is not interesting for our talk, but this is needed for the proofs of our results. But here is our main result. So this operator is topologically semi-transitive on A, if and only if for every fixed P alpha. So P alpha is taken out from this net here. And for every fixed element from this net, there should exist a strictly increasing sequence of natural numbers. And the sequences QK and DK in A such that these limits are 0. And in addition, this limit is 0. So I multiply these norms, and when I multiply them, the product should go towards 0. And then if you look at this result, this is a very general algebraic result, and we are interested in concrete examples where we have where these conditions are satisfied. This is so far a very general abstract algebraic result. But I can promise you, and you will see now in the next slides, that we really can construct out of these general conditions very concrete examples where these conditions are satisfied. Let us first consider commutative C-star algebras. And due to the Gelfand-Naimark theorem, all non-unital commutative C-star algebras are of this kind here. So if X is a locally compact Hausdorff space, then we can simply consider C0 of X, which consists of all continuous functions on X, vanishing at infinity, and which is, of course, equipped with the supremum norm. And then this non-unital C-star algebra will be close ideal in the unital C-star algebra CB of X. And what is that? This is the C-star algebra of all continuous bounded functions on X equipped with the supremum norm. And now in this connection, a very important set for us will be CC of X, which is the space of continuous functions on X with compact support. So, as I said, in this case, A is C0 of X, A1 is CB of X. And what is phi? What could be interesting phi in this case? We can consider phi of F be given in this way here, where alpha is a homeomorphism of X. So you have a homomorphism of X, and then your isometric star isomorphism of this C-star algebra and also this C-star algebra is simply that you always take a composition of the function with this alpha. And now if we consider this set of all continuous compactly supported functions which are between 0 and 1 and which are exactly 1 on some compact subset of X, you can also consider S tilde consisting of F squared, where F is in S. It is not hard to see that actually then S tilde is simply equal to S. And then this set is actually an approximate unit for C0 of X due to the Urison's lemma. Then we can actually, this set will actually be our desired set, which we consider it in this general setup, this P alpha. You can simply index it by, you will have a relation on this, it will be a directed index set simply by letting F G greater or equal to F. It is not hard to see that. But now we have some more concrete C-star algebra. And then our general conditions, which were introduced here, will reduce to some more concrete conditions. What is that? So we should require, in addition, that alpha, our homeomorphism alpha, is aperiodic. What this means? This means that for each compact subset K of X, there should exist some constant depending on this K, such that for each n greater or equal to nk, we have that K intersected with alpha n of K is empty. In the literature, people use also the notion runaway instead of aperiodic, but some people use aperiodic. And then you can see that if this condition is satisfied, then for every F in this S, which was defined here, for every F in this S, there will exist some natural number n depending on F, such that phi n F multiplied with F is 0 for all n greater or equal to nf. So then you see actually that we come back to our requirement here. We recall that we have this requirement on our isometric star isomorphism, and this requirement is then satisfied if you put the condition that your homeomorphism is aperiodic. Do such homeomorphism exist? Well, of course, yes, because if you take X simply to be equal the real line, then every translation is actually aperiodic in this sense. So we do have these isometric star isomorphisms in this concrete case, which satisfy our general requirement. And then our general conditions, which we had here, by some calculations, one can check that they reduce to these conditions. What is that? For every compact subset K of X, it should be not omega, sorry, this is a misprint. For every K compact subset K of X, there should exist a strict increasing sequence of natural numbers such that the limit of the products of these supremums, where we take supremums over the respective compact subsets K of these expressions here, the product of these supremums should tend to 0 when K goes towards infinity. All these conditions in the previous theorem, which we had here, reduce just to this. And this is something which allows us to construct concrete examples. Already on the next slide, I shall introduce you the concrete examples. So here alpha is an aperiodic homomorphism, and now B is a function. Because recall that now we consider this concrete C-star algebra. So in this case, the elements of this C-star algebra are simply the functions. So this, this element B here is simply the function on X. And then we have these expressions. And what is our example? Okay, as I said, let X be equal to R, and alpha be a translation by this. Alpha of t is t minus 1 for all t in R. And then let B be a continuous, any continuous bounded positive function on R, satisfying that B inverse, that it is invertible, and that B inverse is also bounded. And if it happens that you can find some constants m delta k1, k2 greater than 0, such that m minus delta is strictly greater than 1, and such that B of t lies in this strip here for all t less than minus k1, and B of t lies in this strip here for all t greater than k2, where k1 and k2 are arbitrary positive constants, then the conditions which we have here are satisfied. It is not hard to check. Similarly, if you turn around and you consider alpha to be t plus 1 for all t in R, and then you require that B delta lies in this strip here for all t less or equal to minus k1, and B of t lies in this strip here for all t greater or equal than k2, then also these conditions which we have here are satisfied. Moreover, if we return back to the case when alpha of t is t minus 1, we can also require that B of t lies in this strip here for all t less or equal to minus k1, and B of t lies in this strip here for all t greater or equal to k2, then again, these conditions here will be satisfied. And the last case is if alpha of t is again t plus 1 for all t in R, but we require that B of t is in this strip here for all t less than minus k1, and Bt is in this strip here for all t greater or equal to k2. Then also these conditions here will be satisfied. It is not hard to check by the calculations. Of course, when I read now, it is maybe not easy to follow, but once one draw the picture, then one can see actually that a very large class of functions are within these conditions, because we consider arbitrary constants k1 and k2, and we just require that b of t are in these respective strips, and nothing more than that. Continuous functions, I mean, b are in these strips. So what I want to illustrate by this example is simply to say that actually a large class of functions, and thus a large class of these operators, which we consider here, satisfy these conditions in the concrete case of these commutative non-unital C-star algebras. But one can ask, okay, so far we have just considered commutative C-star algebras. What happens in the non-commutative case? And for that purpose, we shall consider some concrete non-commutative C-star algebras. Okay, let H be a separable Hilbert space with an orthonormal basis indexed by Z, and we can let U be a unitary operator on H. And then what can we consider as an isometric star isomorphism of this C-star algebra B of H? Well, it can simply be given in this way here. So you multiply from the right by U and from the left by U star. But now you recall that we had some special conditions on our isometric star isomorphism phi. So in this case, we should see what are these conditions in this concrete case. Okay, so first of all, my A, in this case, non-unital C-star algebra, will be the C-star algebra of all compact operators on H. And then, as you can guess, A1 will be B of H, because A is a closed two-sided ideal in B of H. And what can be the desired net which forms an approximate unit for A? Okay, for each M in N, let Pm denote the orthogonal projection onto this span here, span from E minus M up to EM, where EJs are taken from this basis here. So simply we start from E minus M and up to EM, we consider the span of these vectors from this orthonormal basis, and then we let Pm be orthogonal projection onto this finite dimensional subspace. And then it turns out that the set of all these projections where M runs through natural numbers is an approximate unit for B0 of H. And in fact, it calls for more general C-star algebras, even for the C-star algebras of compact operators on the standard Hilbert C-star module, and not just for the separable Hilbert space. This is a result from the book by Manuilov and Troitsky on Hilbert C-star modules. But in this talk, we shall just consider Hilbert spaces, not Hilbert C-star, general Hilbert C-star modules. So, okay, so A is B0 of H, A1 is B of H, and then we have this net consisting of orthogonal projections, which simply projects H onto these subspaces. But now you recall that we required that our isometric star isomorphism phi should satisfy this condition for every fixed P alpha from this net. Now P alpha, what is this net? As I said, this is simply Pm. So for every fixed Pm, we should have this condition to be satisfied. So for every fixed M, in other words, for every fixed M, we should be able to find some constant Nm, such that for all n greater or equal than Nm, this relation should be 0 for all n greater or equal to Nm. And this puts automatically some conditions on our unitary operator U. Because actually, if you write out this, it simply means that you want that Pm, Un Pm is 0 for all n greater or equal to Nm. So you should be able to find for every fixed m, such nm, such that this relation is satisfied for all n greater or equal to nm. And this is a very special requirement on our unitary operator u. And then one can ask, do there exist such unitary operators u? And fortunately, the answer is positive, and the whole class of such unitary operators exist. How is that? Well, because if you let alpha be a translation on z, and you define your unitary operator u to act on this orthonormal basis ej simply by this way here. So u alpha ej is equal e of alpha j for all j is z. U alpha is just the notation. So I let U alpha be the operator which acts on this orthonormal basis Ej in this way here. And from this definition, you see that this is a well-defined unitary operator on H because it sends the orthonormal basis on itself. But not only that, actually, since alpha is a translation on Z, it is not hard to check that U alpha actually satisfy this condition. So for every fixed m, I can find a large enough nm such that this relation is satisfied for all n greater or equal to nm, which will automatically give me the desired relation on my isometric star isomorphism phi, because my phi was simply defined in this way here. Okay. So then you see that in this non-commutative setting with alpha b0 of h and alpha 1 b of h, and with phi defined in this way here, and with this net pm, I am able to satisfy my general requirements from this setup here. And now we can look at how will these conditions, general conditions, look like in this very special, concrete, non-commutative case. Okay, they will look in this way here. So these conditions, these general conditions, are equivalent to the condition that for every m in n, there should exist a sequences of operators in B0 of h, and a sequence of natural numbers, strictly increasing sequence nk of natural numbers, such that these limits are 0, and also that this product tends to 0 when k goes towards infinity. And so far it is nothing mysterious. This is just translation in this language, in this concrete case, of these general conditions. The first one are exactly the same. The second is just when you apply these calculations on your concrete isometric star isomorphism phi, which is given in this way here. So far, this is still very hard to construct some concrete examples. But fortunately, one can show that if you have another conditions which are slightly stronger but easier to calculate, then these conditions also provide that these conditions here are satisfied. What are these new conditions? Okay. So now we are approaching something which is known in the literature as supercyclicity criterion. And what is that? Okay, so if there exist dense subsets H1 and H2 of H, and a strictly increasing sequence nk of natural numbers, such that for every f in H1 and every g in H2, this limit in 0, then it turns out that this condition is so strong that actually once you have this condition satisfied, then also these conditions will be satisfied. And when these conditions are satisfied, then our operator will be topologically semi-transitive. I am sorry, I should just say that before speaking about this, I should say that actually you can consider T with respect to this F phi, with respect to this phi, where phi is defined in this way, and where your element B, recall what is B? B is here the left multiplication, where your element B, where your element B is VU. So I have the concrete isometric isomorphism phi, which is given by phi of F is equal U star FU. And then I can also multiply from the left by element WU, where W is an invertible bounded linear operator on H. So I choose an invertible bounded linear operator on H. I consider this operator here, which is nothing else but this. So it is just another notation T tilde of UV, but this is the same as this operator here. And what is that? It is actually, when you calculate, you can see that this is actually WFU, which acts on B0 of H. And for this operator here, as I said, if these conditions are satisfied, then by our very first theorem in this talk, this operator will be topologically semi-transitive on B0 of H. But as I said, these conditions are still quite general. So we would like to consider these conditions here, which look like the famous supercyclicity criterion. And when you have these conditions here satisfied, then your operator here will be topologically semi-transitive on B0 of H. And as you can see, these conditions here depends solely on your invertible bounded operator W on H. And okay, now I can, thanks to these conditions, provide you some concrete examples. So, if H is L2 of R, and V is the operator on H, which is defined in this way here. So what is W? W is actually weighted composition operator, where alpha, you take alpha homomorphism of R, and you let B be a continuous bounded positive function of R, such that B inverse is also bounded. If you have such B and such alpha, you can define W in this way here. And then W is an invertible bounded linear operator on H. So we can consider the operators of this kind and then ask, when are these operators topologically semi-transitive, or in other words, when will the operators of this kind satisfy our requirement here? In order to say something about this condition here, we should first observe an estimate. So if you let M be in N, and you choose any F in L2 of R, so in our Hilbert space H, such that the support of F is included in this interval here, then by some calculations one can actually check that for all natural numbers N, this estimate holds, and also this estimate holds. And then what happens? Well, for every F and G which are compactly supported continuous function on R, this expression will be less or equal than the product of these supremums here times this norm, where M in N is chosen in a such way that the support of F and support of G is included it should be the closed interval from -M to M. Of course, this is possible because F and G are, by the assumption chosen, to be compactly supported. And then since they are compactly supported, we can find such M such that the support of N, support of G are included in the closed interval. So sorry for these brackets, it is supposed to be a closed interval from -M to M. And then if you choose such large M, then one can check, thanks to this estimate here, that this product is less or equal than the product of these supremums, times these norms. And certainly, since this inequality holds, then also when you let n goes towards infinity, then certainly also the limit will be less or equal than this limit here when n goes towards infinity. Of course, one can ask, does it make sense to speak about limit? Does the limit exist? But in fact, yes, if you consider very special alpha and b, which have been constructed in our very first example here. So the reason for speaking about all this is that actually always we can cook it down to this concrete case here, and you see that now our example here does not only provide the class of topologically semi-transitive operators on this commutative C-star algebra, but thanks to this result here and this estimate here, we are now able to use this example, which we had here, to construct also topologically semi-transitive operators of this kind, operators on the non-commutative unistyle C-star algebra B0 of H, which is the C-star algebra of compact operators on H. Because then we simply let W be the weighted composition operator on L2 of R. If we consider H to be L2 of R, then this will be satisfied. Okay, here so far we have been speaking about C-star algebras, but also we want to speak about other Banach algebras, which are not necessarily C-star algebras. And before speaking about this, yes, I would just like to mention that actually here, the Hilbert space does not need to be separable, because this net will still be an approximate unit for B0 of H. So actually we don't need separability of H. Okay, so far we can be speaking about C-star algebras, but now we want to speak about also some other Banach algebras which are not necessarily C-star algebras. Okay, so we can let now A be C0 of R, and we can choose tau be a bounded continuous function on R. And then if you define alpha tau to be all f in A, such that this series is finite, then it turns out, and if you put on this set this norm here, then it turns out that this set is actually a Banach algebra under this norm here. And it is not my result, it is an old result proved by Takahashi. And then you actually, by this, if you consider this norm and this set, then this set under this norm is a Banach algebra. And we will call this algebra Segal algebra, corresponding to this function tel. And then we want to consider a compact subsets K epsilon tau. Why do we use notation epsilon tau? Well, because these sets are not supposed only to be compact subsets, but compact subsets of this set here. So therefore, since we here have involved tau and epsilon, we want to use this notation here. Okay, and then we want to consider weighted composition operators on this Banach algebra. And then if V is a positive function on R, such that it is continuous bounded, and also such that W inverse is bounded, and you let tau be, as I said, a bounded function on R continuous, and you let alpha be a homomorphism of R, such that this relation holds, that tau composed with alpha is equal tau, then the operator T tilde alpha V defined in this way here, so weighted composition operator, is actually a bounded linear self-mapping on A tau. It is due to this requirement here. Of course, it is straightforward to see that we have many examples satisfying these conditions, because simply if alpha is a translation by, let's say, 2 pi, and you let tau be some trigonometric function, then this will be satisfied. So it is not hard to find examples satisfying this condition. But we also choose a positive function double v with this requirement. Then we consider this weighted composition operator, which turns out to be a bounded linear self-mapping on A tau. And then it makes sense to speak, ask, when will this operator be a topologically semi-transitive on A tau? And here are our conditions. So for each positive epsilon and every compact subset k epsilon tau included in this set here, we require that there should exist a strictly increasing sequence of natural numbers such that the limit of the products of these supremums is 0, where we evaluate supremums over this compact subset k epsilon tau. And now you see straightforward that actually this is weaker than what we had in the beginning of our talk when we consider this, the product of these supremums, because here we consider it arbitrary k, but here we only consider special type of these compact subsets k. So you see then directly that actually our construction from this very first example here also produce topologically semi-transitive operators on this Segal algebra, topologically semi-transitive weighted composition operators on this Segal algebra. If you let your double V simply be equal your function B constructed in this example here, and you let alpha be a translation. What I want to say that the example which I introduced in the very beginning of talk can be used to construct topologically semi-transitive operators on various C-star algebras and Banach algebras, and not only for same weighted composition operators on C0 of R. Then at the end, I just also want to say something about the adjoint. Because you recall that in the beginning of our talk, we have been speaking about weighted composition operators on C0 of X. Okay, let me just put back again to the very first slide. So we wanted to study the operators which are weighted composition operators on C0 of X. Yes, you see here. But now one can ask, okay, what happens with the adjoint? And can we say something about when the adjoint is topologically semi-transitive? Then we should recall that C0 of omega, if omega is a locally compact Hausdorff space, what is the dual space? The dual space is the Banach space of all radon measures on omega, which is equipped with the total variation norm. And then if your operator T alpha V is a weighted composition operator on C0 of omega, then you can explicitly calculate the adjoint. And the adjoint will be given in this way here. So the adjoint applied to a radon measure and then evaluated in a Borel measurable subset C of omega. It looks like this way here, where this measure mu composed with alpha inverse is due to the standard notation here. And I shall not stick into details, but I just want to say that also for this case, we can say something about when this operator is topologically semi-transitive. Well, in this case, the equivalent conditions are that for every compact subset K of omega and any two measures mu v in M of omega with this assumption here. So we require that the total variation of this measure disappears on the complement of K. For any two such measures, there should exist a strictly increasing sequence of natural numbers and the sequences of Borel subsets AK and BK of K, such that this is satisfied. Of course, this is not hard to be satisfied if you take alpha to be aperiodic, but in addition, we require that these limits should be zero and that the limits of this, the product of these supremums should be zero, where now the supremum are taken over these subsets AK complement intersected with K and BK complement intersected with K. And here, once again, these are the total variations of the measures. And now you can say that, okay, but it seems that these conditions are very hard to check because we have some arbitrary Borel subsets where these conditions should be satisfied. The reason for having so artificial conditions is because we wanted to really explain what are the equivalent conditions to semi-transitivity of this operator. But fortunately, if you strengthen a little bit this, then you lose equivalence, but you get some conditions which are easier to check. And what is this? Well, these operators, the adjoint of weighted compositions operators, will be topologically semi-transitive on n omega if these conditions are satisfied. In other words, if the product of these supremums tends to zero when n goes towards infinity, where the supremum is taken over a compact subsets K. And not, now you see here we consider it some strange subsets, but here we consider just the compact subsets. And of course, these conditions are stronger than these conditions here, but the advantage is that these conditions are easier to handle for the concrete examples, because now I just consider compact subset K, and I no longer bother about this relation here, about finding some sequences of Borel subsets satisfying this and also satisfying this. And at the end, as I promised, you can actually construct in a similar fashion concrete examples satisfying this condition here, but this is not exactly the same as the example which I introduced in the beginning of the talk, but somehow symmetrically opposite. So it is in a similar fashion, but you just turn around the whole thing. And I think it is not necessary to read once again all this construction, but I just want to say that it is possible to obtain this construction. And also one important thing before I end up my talk is that you have noticed that I have always pushed this assumption that homeomorphism alpha is aperiodic, which in our concrete cases were actually some translations. But actually, if you consider this corollary here, where you have only these sufficient conditions, for these sufficient conditions, you don't even need to require that your homeomorphism alpha is aperiodic. So actually, aperiodicity was only needed to obtain equivalence here and to obtain the equivalence here and so on. But also in the very first theorem, general theorem, this assumption on our isometric star isomorphism that this relation holds has not been needed, in fact, to prove that these conditions in I imply I. So we only needed this to prove that I implies II. But to prove that II implies I, you do not need this requirement on your isometric star isomorphism phi. But we could see from our examples here that in fact, since we considered alpha to be translations, then automatically this condition that alpha is aperiodic and that phi is the desired isometric star isomorphism satisfying this assumption, everything was satisfied. So in the conclusion, I just want to say that, as you can say, our example, which I introduced in the beginning, gives rise to large examples of topologically semi-transitive operators on various C-star algebra, Banach algebras, and even Banach spaces like the space of Radon measures, which we consider it here. So I think I can end up my talk here. For interesting, I have some other results which I can send on the mail. But so far, I would just like to thank you for the attention and for giving me opportunity to present these results. If you have some questions, let me know. Thank you.
Thank you, Professor Ivkovic, and we have time for questions. So please, questions. Yeah, please, Andrei, go ahead. Andrei, can you hear us?
I'm sorry, the microphone was switched out. Thank you very much. And Stefan, thank you very much for the very interesting lecture.
Thank you.
Could you please tell operators of what nature can be, for example, cyclic? For example, are there any examples of differential operators which are cyclic?
Well, in this situation here, we have been focused on bounded operators, and then I think we can move outside of this setup if you consider differential operators, which usually can be also unbounded.
I see. Thank you.
Yes, yes. But in fact, I should just say that in fact, I presented my part of research, but general research which deals with this kind of bounded linear operators on Banach spaces, which are hypercyclic, supercyclic, and whatever you want. Usually I see that people consider operators on function spaces like weighted composition operators. So that kind of operators have been investigated in this setting here, but I was curious to see how the things look like in non-commutative setting, as you could see from my talk. But it is also, as you could see, closely related to weighted composition operators. But I know some results regarding differential operators. I think that Vlaho is the writer, and that she considered, Greek mathematician, she considered differential operators. And in fact, you are right that this here does not actually, how this is defined, topological semi-transitivity, this definition could also work for unbounded operators, not only on Banach spaces, but for general topological vector spaces. And recently I had a paper which is now submitted where I actually consider it unbounded linear operators, right, multipliers on non-commutative L2 space, which has been equipped with another topology, not with the norm topology, but with another topology generated by some positive Sesky linear form and so on. So just to summarize, it is possible to consider this concept also for unbounded operators. And I think you are right that it would be interesting to see what can we say about differential operators in this setting here. But my talk and many other papers are now are limited to bounded operators. So I'm sorry, but yes.
For example, another example, translation operators, they are bounded. Yes. Can a translation operator be cyclic or topologically semi-transitive?
Yes, if you consider translation operators, then actually, at least in this setting here, where we consider supercyclicity or hypercyclicity, which is even stronger, then I think you need weights. So it is not, I think that if you just consider translation operator, it would be cyclic on the space of entire functions. There are some results which my colleague, Professor Zoriana Novosad, if you know maybe her, she considered that setting. But if you consider on other function spaces, which I consider here, for instance, L2 of R, of C0 of R, then you need that you actually have a weighted composition operators. And as you can see from these results, actually, these conditions are expressed in terms of our weight, because this function B is actually the weight function in the weighted composition operator. If this is what you ask for.
Thank you very much again.
Okay, thank you for the interesting questions. Thank you.
Okay, well, Fernando.
Hello, Stefan, thank you very much for your talk. I am very lost. I lose some part of the talk, but I remember that you state a result on general C-star algebra, right?
Yes.
But the topology, what do you use is a uniform topology or weak operator topology?
Because okay, so yes, you are right. In fact, in this talk, I just consider norm topology on the C-star algebra. I should have made it more precise. I'm sorry, but in fact, here, and also you see these norms. Here we consider the normed topology on the C-star algebra, but it is true that we can consider also other topologies, and I have some results, for example, regarding strong operator topology. But in that case, I can send you these papers. In that case, I do not have equivalence, but I provide some sufficient conditions which give me some examples for topologically transitive operators on, for example, B of H, when B of H is equipped with a strong operator topology, or weak star if you consider the dual and the weak star topology and so on. So it is possible to consider.
Because you need separability, no? The hypothesis. So you are using the uniform topology. I think maybe the requirement that the sufficient condition imply separability on the C-star algebra with the uniform topology.
Yes. In fact, it is therefore this was the reason why I introduced both these notions, because this notion of topological semi-transitivity, in fact, works also for non-separable.
I see.
But I think that there is a result, not my result, but another result which claims that topological semi-transitivity is equivalent to densely supercyclicity. But I am not sure. I think that in that case you need separability of the space, because for topological transitivity, if you don't consider semi-transitivity but just topological transitivity, then it is known that topological transitivity is equivalent to hypercyclicity only for separable spaces. So I think yes. But topological transitivity works for general spaces. So yes.
Thank you.
Okay. Well, maybe more questions. I probably have a very quick wondering, maybe not a question, but a wondering. You spoke about composition operator in the sense that you take a function f on which acts and compose it with a function phi. Phi is a symbol. What about the vice versa? If you take a composition operator when phi acts on f, phi of f of x, I'm just switch the functions.
Sorry, could you repeat once again?
I mean the composition operator that you considered, you act on a function f with a symbol phi. Say you consider f composed with phi of x. Yes, that is the standard notion for composition operator. Okay, so.
Yes, I mean, what I do actually here is that I compose f with the homeomorphism alpha of x. Yes.
This is a special function. It's not an arbitrary function. Okay,
Yes,
I see.
So I pick some homeomorphism and then, yes.
So it should be a special function. Okay, I see.
Yes.
Thank you. Well, maybe more questions? Well, I don't see questions, but we not finished yet because we still continue. As I said earlier, Professor Ivkovic is not only good mathematician, he is a great professional piano player who has won more than 30 different awards in Serbia and many other countries. And you see, today is our final seminar for this spring semester. We will have a break for August. So we decided to have a very nice end of this series of seminars. And Professor Ivkovic kindly provided us with a small piece of his work, and we are very happy about it. So let's listen to maybe 1-2 minutes.
Thank you very much.
Okay, you see, our speakers are talented mathematicians, but also they are talented in other very nice issues of life. And many thanks for Professor Ivkovic for excellent talk and for giving us this opportunity to listen to this music.
Thank you very much.
Thank you.
Thank you.